will have, is having any problems with that, please let us know. And we will obscure him and not show to all over the world. Second recommendation, second thing is that for your internet connection, we can use EduRoam, and I think most of you have. If in case it doesn't work, we have also a Congress Wi-Fi. It's called the UCM Congressos, and you should put this user and password. Okay, so that you can find this information also on the Indico of the conference. Okay, that's all for the moment. So I invite here the first speaker, which is Ian Stewart, and the moderator, which is Alexei.
Any special instruction?
It's just, I think it's easy, no? The big one for going on. Mm-hmm.
Okay, it's pleasant for me to open the first session. First speaker is Ian Stewart. Please.
Thanks a lot. So it's a very privileged to give the first talk here at this workshop, and I know a lot of the speakers will be talking about transverse momentum distributions. So what I decided in my talk is to give a motivation for studying transverse momentum distributions as well as an introduction to soft collinear effective theory. There'll be a lot of stuff in my talk that actually is older work. There will be at least one new thing in my talk, but this should help subsequent speakers focus on more modern and sophisticated things without having to give that introduction and motivation. So let me just start out with an introduction to soft collinear effective theory. So this is an effective theory that's the EFT for collider physics, and it describes hard interactions in QCD, which are producing energetic collinear jets or hadrons, as well as soft particles. And it's been used in a lot of different areas, in high energy physics, in nuclear physics, quarkonia physics, and in particular here, transverse momentum distributions will be relevant in my talk, as well as sort of higher power. So subleading power over here. There's a review article that I wrote recently that you can refer to if you want to get an introduction to sort of some of the more things that go beyond what I'll say in my talk, or if you want to see more references. So how does the EFT work? So if you have, for example, two jets producing three jets in a pair of leptons, we would be writing down collinear fields for each of those, both the incoming directions as well as the outgoing directions. And those collinear fields in the low energy theory are going to be decoupled from each other. They're interacting with each other only through the hard interaction. And there's also soft fields that can interact with the collinear fields. So this is what the quantum field theory looks like. We have scaling, both collinear scalings for the collinear particles, soft scalings, which could be lambda, 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 or lambda squared, lambda squared, lambda squared. Lambda is a small parameter here, given by the process that you're studying. And then there's some off-shell effects, which you integrate out. We make use of light cone coordinates, which I guess everybody's familiar with, but we have different if we have multiple directions, we might have different light cone coordinates for different directions. In this case, we have 5 of them, which we could at least eliminate one of. The effective theory is organized as a power expansion in this lambda. And we just have an effective Lagrangian. At leading order, that's what the superscript means, that this is leading order in lambda. At leading order, we have both dynamical terms that tell how the modes in the effective theory talk to each other, as well as sort of modes, interactions that came from integrating out the hard physics, which were at the sort of center of the diagram here. So both how the subsequent evolution and emission of radiation in these jets happens, that's in the L0, and then the L hard has this sort of hard interaction, and it typically only appears once in the process. There's also factorization violation, and factorization violation in this effective theory is given by a very special Lagrangian known as the Glauber Lagrangian, and all factorization violation only occurs through that Lagrangian. And other than that, you just have a power expansion, so there's higher order Lagrangians, higher order hard interactions. Those don't violate factorization. It's only this leading order Glauber Lagrangian that could violate factorization. So if that leading order Glauber Lagrangian can be shown to be absent or not having any effect on your process, then you'll have factorization. And I'm not going to really discuss this Lagrangian today. We'll just be assuming essentially that it cancels, and in many cases it's been proven to cancel. So if it's not there, then you just have an expansion in lambda, both in your hard interactions as well as in your dynamics, and you can factorize at any order in the power expansion. Okay, so this is what the effective theory is. What's the effective theory built out of? So it has what are called quark, jet, or parton fields, chi-n, which is a quark field in a particular collinear direction dressed by a Wilson line that came from integrating out hard interactions, or the analog for gluons, which is in the adjoint representation. Those are the building blocks. We build operators out of them. We have definite power counting in lambda for them. It looks like a twist expansion, except it's more general than a twist expansion. It turns out that you only need 3 objects to build any higher power operator in the collinear sector, just the quark and gluon fields as well as the transverse derivative. Other things can be eliminated with equations of motion. And the soft sector looks like equations of motion just for the full theory, so I didn't try to simplify that. So if you have some process, say 2-jet production from PP, you might have 4 different directions. If you go to subleading order, you could just add, say, one of these Bs, and so you'd have 2 fields in the same direction. That would be a subleading power. So here's it in pictures. Here's for E plus E minus. 2 jets at leading power would just be 2 quarks. If you want to go to subleading power, you could add an extra gluon field in the hard operator. Or you could have some subleading power Lagrangian that gets inserted, and that would give you a subleading power interaction. So what are these subleading powers that I'm talking about? So leading power, if I look at some cross-section, differential in some tau variable that's small, the leading power would be a bunch of logs, or logs divided by tau, if I divide by that tau, which are some plus functions, as well as a delta function. And then the subleading powers are just suppressed by 1 power of this expansion parameter. So this could be transverse momentum in the case of TMDs, it could be thrust variable if you're doing thrust, etc. This is what people call next leading power in the perturbative regime, where I would be thinking about like maybe predicting these things because I'm interested in perturbation theory and understanding what the coefficients here are. And maybe I'm interested in summing these logarithms. Oftentimes people don't do that. They don't do the resummation here. They do the resummation here at leading power. They have some factorization theorem, and this is treated as a correction. And it's often treated as a correction where you just use fixed order perturbation theory for it. And that basically amounts to summing the entire series of next to leading power, next to leading power, next to next leading power, the entire series, but working at a fixed order in alpha. And you're just doing perturbation theory in alpha. When people do that, they call these non-singular corrections. I'll talk a little bit about those. There's another place where next leading power corrections are relevant, and that is when you think of non-perturbative corrections. So not expanding in some perturbative regime where we can have an alpha S, but expanding in some region where the next leading power correction is given by a higher power of lambda QCD. Lambda QCD being much less than some perturbative scale. We have sort of a leading non-perturbative distribution and then a subleading one that has an extra power of lambda QCD in it. It's not like it's either one or the other. Oftentimes we have both of these. So that's what we mean by going beyond leading power. Leading power is sort of the first term in some expansion, and next leading power is higher order terms. Let me now switch to TMDs and do some review. So what are we interested for transverse momentum distributions? We're interested in both parton distribution functions, distributions of the proton in for example, a PP collision or an EP collision. And we're interested in probing it in 3 dimensions. So not just the longitudinal, which is the collision axis, but also transverse to that, as shown in this figure. And that's what these transverse momentum dependent parton distribution functions are, or their fragmentation analogs in the final state. And the typical processes, although you'll hear other processes discussed in the meeting, the canonical processes are semi-inclusive DIS or CITIS, Drelian, and dihadron production in E plus E minus. And these probe either a pair of PDFs, a PDF and an FF, or a pair of FFs. And to probe them at small transverse momentum, for example, when the transverse momentum is what are lambda QCD, then you were getting access to new non-perturbative information about the proton, which is in this TMD PDF. That's one of the goals here. And so we're looking with TMD factorization always at small transverse momentum, but we could be also looking at a region where transverse momentum is perturbative, and then we just have to calculate in a sort of a hierarchy of scales the dependence on the transverse momentum. So there's 8 of these distribution functions in the PDFs, in the quark PDFs, also in the gluon PDFs. They have various names, unpolarized, Sivers, Wormgear, etc., and that's based on their cataloging in terms of this polarization, both of the operator here, the quark polarization of the operator, as well as of the state, here the nucleon state or proton state, whether it's unpolarized, longitudinal, or transverse, and then you get various different distribution functions, which encode, for example, correlations between spin and angular and orbital momentum of the quark inside the proton. So there's a lot of physics here. It's kind of like probing the hydrogen atom and looking at the fine structure. And that's what TMD physics does for us. And how do we probe it? Well, we probe it with observables. We look at observables as functions of angles. So here in the Drell-Yan process, we're measuring both this theta in this CS frame here with the hadronic plane defined by the hadrons and the leptonic plane defined by the leptons. We look at some angles between things, also the angle to the spin vector. And we can do a full decomposition in terms of structure functions, and then the TMD factorization predicts those structure functions in terms of the objects on the previous slide. TMD PDFs in the case of Drell-Yan, and a product of a TMD PDF and FF in the case of CITES. So if you want to learn more about this, let me do a little bit of advertising. We have this TMD handbook written by various people, including many people that are in the audience here. And it reviews all modern TMDs, including different ways of defining them and different ways of doing calculations, as well as including lattice QCD, phenomenology, jets, etc. So let me just give you a few brief highlights that are relevant things for this meeting. So we have rigorous factorization theorems that have been proven to all orders in perturbation theory, and these connect cross-sections to TMDs. And as I said, there's here's a cross-section, there's some hard region, and then there's some parton distribution function, in this case a transverse momentum parton distribution function, but here written in terms of transverse position rather than transverse momentum, so just a Fourier transform. It's constructed out of sort of matrix elements that involve the proton state as well as some soft overlap terms coming from the soft region. It's tractable in lattice QCD. I'm not going to discuss this here. The universality of the leading power transverse momentum distributions is understood, and there's an interesting sign flip that happens for the T-odd ones that is probing final state interactions. The evolution of these objects is also very interesting. It's a two-dimensional evolution. There's sort of two parameters that we can evolve in. One is an evolution in the usual mu, so invariant mass. One is kind of connected to rapidity, which is in this formula here is this theta given by the Collins-Soper kernel. And so there's some evolution equation where you have some boundary condition at some low scale where you might have specified a model, or you might have done some lattice calculation at small mu 0 and zeta 0, and you can evolve it up to with these anomalous dimensions, but there's two of them. And then there's also, if you're in the region where the transverse momentum is much bigger than lambda QCD, then you would calculate the dependence on BT or QT perturbatively, and you'd have to only deal with the non-perturbative physics when BT inverse becomes of order lambda QCD. In general, you want to do both, and so there's some way of connecting that and putting these things together. So that's also part of this program. So let me spend a little bit of time on non-singular terms. This is how do you deal with the fact that you did this nice resummation for small transverse momentum, but maybe you also want to deal with the region where the transverse momentum is large. And the obvious thing to do is the follows. You define at each order in alpha S the corrections, the things that you're missing in your resummation, as just the full fixed order cross-section at some given order minus the terms that you have in your singular cross-section. Take your resum formula, expand it back out in alpha S, determine this singular F fixed order term, and then determine the non-singular term. And then you would just like to add it. Now the issue is that you can't just add it. If you just take your resummed result and just add that, you'll start making big mistakes. And the reason is that you'll be still doing the resummation in the fixed order region. So you have to do something else, you have to do something further, and that is that you have to turn off the resummation when you go to the fixed order region. Okay, so it's not just enough to add this to your resummed result, you also have to turn off the resummation so that you can sort of get back the full fixed order result. You want to turn off the resummation so your resum will cancel this term and you'll get back to fixed order. So this is acting like a power correction in the resum region, but you'd like it to just give back fixed order in the fixed order region. In SCT, this is solved by what are called profile functions, which are just making the scales mu turn off the resummation when you want to turn it off. And that's a very well studied problem, and people use it in all sorts of processes. In TMDs, it's a little special because in TMDs, the resummation is simple in impact parameter, in BT space. But you'd like to make predictions in QT space to compare to experiment. And so you want to sort of have a resummation that uses BT, so you might have scales that are set by BT, running from, say, BT inverse up to Q, but you'd like to control the scales in QT space. And so you have sort of what's called a hybrid profile that might look like, as shown in this plot. So if QT is small, then your BT profile, your mu scales, are just following sort of a straight line, which is given by this formula. Slope here, I'm plotting 1 over BT, so slope is 1. And then if your QT is large, you just have all these scales at the scale Q. So it's flat. And then you have some way of transitioning between those two so that everything is smooth. And this is a way in which you can sort of guarantee that you're not making mistakes in the fixed order region. And it's a well-studied problem. Here's an example of using it. So this is an example from Drell-Yan, just at next leading order with next to leading log resummation. And so shown in red is the next leading order curve, which of course has the characteristic 1 over QT blow up at small qt. The resummation given by the red cures those divergences, Sudakov resummation, et cetera. I'm plotting qt d by dqt, or d log qt here. And the non-singular terms are shown in green, and you'd like actually for when your qt gets large, here I'm plotting at the z-scale, so when qt gets large, you'd like your blue curve to kind of go back onto your green curve, and so your blue curve to go back onto your red curve, and that's what you see happening because the resummation is being turned off in this region where the green is growing. And of course, for the z-scale, the green is always pretty small, but it gets bigger if you go to smaller q. So here shown is q equals 20, and you see the green is now a larger portion, and you sort of have to turn off the resummation much earlier if you're at smaller q. So this is just an example of how this works. And then we get controlled uncertainties, not just in the resummation region, but also in the region where we are now going back towards fixed order. We still have uncertainty bands here, and they just reproduce fixed order uncertainties. There's another interesting kind of perturbative type of power correction, and that's fiducial power corrections. When you deal with experiment, you have to make cuts. For example, your lepton might have a minimal PT, and there might be some rapidity cuts. When you make those cuts, you can change the nature of the power expansion. Sometimes you just change it completely and you have to rethink the problem. And sometimes you don't, but even in the cases when you don't, you can still change the size of the power corrections. So generically, you end up something that might be suppressed by qt squared over q squared gets enhanced by a power to qt over q. That's exactly what happens in Drell-Yan. If you put cuts on the lepton and you consider, for example, this gray, which has those cuts included, you can see that the slope of this curve is 1, corresponding to this, whereas without those power corrections, you'd be in this green, which is slope 2. So it enhances the power corrections to think about cuts. And a nice example of that is actually what's called the PT lepton spectrum in Drell-Yan, producing a W boson to lepton neutrino. You can't measure the neutrino, you measure the lepton momentum, and you use this, for example, for W mass. This spectrum is actually still dominated by small qt, so you still want to do TMD resummation. Here is shown the leptonic phase space of PT lepton for a given qt, and you see sort of for the blue with qt equals 0, and a very sharp peak at half the W mass, it's blowing up. And then in red, you see what happens if you have some non-zero small qt. And so you're dominated by the sort of region of small qt, which is these curves. And there's another variable here, which is how far away are you from the peak? This peak is at half the W mass here with the blue, and how far away from that are you? You don't want to be perturbative in that variable. You'd not like to expand in it. So you have to treat that physics exactly. And if you do that, you can sort of get around the fact that fixed order results for this type of cross-section have this problem at this peak, where the PT lepton is equal to half the W mass. If you turn on and do the TMD resummation, then you cure that problem, and everything is nice and smooth and convergent. Okay, so this is just another example where if you weren't careful about these fiducial power corrections and you were to make some expansions in your leptonic part of your phase space, you would have problems with this. So I'm going to go a little bit more quickly since the time is short. So why study next leading power factorization? So there's motivations from universality, motivations from factorization, motivations from getting higher precision, and I'll talk about here some TMD motivations. There's been a lot of progress on this. You'll hear about it during the meeting. There's like examples of things where the first leading log resummations were done for Sudakov form factors. These not in TMD, but in a different case. And both quarks and gluons play an important role there. You'll hear about endpoint singularities later from Matthias's talks. You'll probably hear about subtractions in various talks. And we already saw the sort of decomposition of CITES, but at next leading power, you get access to new structure functions, and that's very interesting. And there's been a lot of work on this. You'll hear about this in the subsequent talks to mine, so I won't kind of go through this. But I will give you sort of an introduction from the point of view of SET. And TMDs at next leading power are basically probing what's called a quark-gluon-quark correlator. That's the new non-perturbative information that one can probe, and they're very interesting objects. So how does it work? In SET, we have the leading power factorization in terms of hard, linear, and soft components. And then at next leading power, we just systematically correct sort of both Lagrangians as well as currents, as I mentioned. So here's the corrections to the linear currents. We either have a p-perp or a b-perp, that's all there is. So we have a p-perp subleading power operator or an operator with a b-perp. There's this one you can prove using reparameterization variance, has the same leading power Wilson coefficient. This one has a new Wilson coefficient. There's also soft next leading power currents, and they could come from various places. Many of them vanish for TMDs. There's one that's kind of interesting involving what's a kind of an analog of the collinear object, which is soft field strength dressed with Wilson lines. It's actually generated by two different regions, a hard region and a hard collinear region. And that's kind of a relevant point in my talk here. So hard region is everything of order Q. Hard collinear is some kind of intermediate region here, which has like the soft plus momentum and the collinear minus momentum. So it's in the middle. And when you go through SET and derive sort of the structure of the operator, you get both contributions from the hard that look like this. They have the leading power coefficient, just a BS perp and some Wilson lines. And then you have something from this hard collinear region that actually comes with an additional jet function. And the type of diagrams that would be generating this second term would look like this, so where you have like some soft emission from the collinear, and you go through and calculate this loop, and it's giving you something at this scale that's Q times the plus momentum of the soft or minus momentum of the soft. So it's intermediate between the low scale and the high scale. And that's very nice. This turns out this jet function here, actually, the sign of the argument depends on whether this is an incoming diagram, like this one, or an outgoing diagram, like that one. This is like the one piece of new information in my talk, because this is relevant to talking about factorization at next leading power. And that is because in our older paper, we had this nice argument about why the soft distributions cancel. And that cancellation actually requires the arguments of these two pieces that come from the two different parts of the soft function from incoming and outgoing to be equal. So the PS minus and PS plus both have to be equal. And then you can use parity, charge conservation, Poincare invariance to make them cancel. So they have to have the same dummy variable here, PS hat, and then the symmetries are sufficient to show that this soft function cancels. It always cancels for the hard region, and that's because that argument, PS hat, didn't show up in this object here. So this one always cancels, but this one here is more problematic. It starts at order alpha squared, and it actually only cancels if you have the same argument, which happens for Drell-Yan and E plus E minus, but doesn't happen for CITES. In CITES, you actually have the opposite sign in this jet function, so you can't simply just add these two objects, and therefore you can't use this formula, it turns out. So that's an extra term in CITES. So when we go through the factorization theorems for Drell-Yan, E plus E minus, and CITES, for Drell-Yan, these are bare factorization theorems. For Drell-Yan, we get contributions from the p-perp term, the bn-perp term, no soft contributions other than sort of a leading power soft function that shows up. And when we do E plus E minus, it's very similar. Now there's also some kinematic corrections, p-perp terms, b-perp terms. but no soft terms. And when we do CITES, it turns out that there's those types of terms, but there's also a contribution from this thing that I just mentioned to you with the opposite signs. So there's an extra term. This is all at the bare level. You'll see in the talk coming after mine what happens when you start thinking about renormalization, and I'll just foreshadow the fact that this term's not going to go away. It's still going to play a role there, but that's it. Thanks.
Thank you. So please ask questions.
Very nice talk. I don't remember which number when you talk about W. Can you go back that slides?
When I talk about what? Sorry.
W measurement. W lepton mass distribution.
Oh, PT lepton.
Yeah.
Yeah.
Yes. So I mean, Taiwan, or I think it's CDF, DZR together, I don't remember. So they use response.
Yeah.
My question to you is that your curve is similar to response, or you actually found your curve is different from response?
I mean, I think Resbos should do this resummation properly, but I can't remember exactly. This also has to do when you do resummation also with how people define a recoil scheme, right? So there's a lot of, like both Resbos and others use different recoil schemes. I don't remember off the top of my head which recoil scheme they are using, but under the assumption of a certain recoil scheme, which is basically the interplay between the QT and the PT lepton and how you treat the leptonic phase space, you want to basically treat the leptonic phase space exactly without any approximations. And as long as you do that, you'll be safe here.
Okay. So maybe Andrzej is going to talk about the power correction. So let me ask you on this. So what you guys found is that the soft factor for the subleading contribution, leading power contribution, is different from leading power soft function.
Yep.
Okay.
Yeah. So at leading power, you have just this kind of square root S that showed up somewhere in my talk. I mean, it's showing up here, sort of the S dagger S. That's the leading power one. And then there's like another one, and this involves a field strength as well as sort of your S dagger S. So it's an extra gluon field strength inserted on the lines, and so if you think of just Wilson lines without the quarks attached, there's an extra soft field strength inserted on the connected object. And that in our first paper, we didn't actually notice this sign difference between CITES and Drell-Yan that I'm now emphasizing in my talk. And so we said it canceled because of this argument, but it actually only cancels for Drell-Yan and E plus E minus, not for CITES.
Are there more questions? Yes.
I just want to ask, so this hard linear mode that you show like 1 or 2 slides before the end,
Yeah.
could I have known from the beginning that I should expect this to show up, or?
Yeah.
Yeah.
Yeah. So I mean, these diagrams are there in SCT1. When you do your matching onto the statement is when you do your matching onto this BS perp, right? The operator is kind of non-local because you have the soft scale here, linear scale there. You can form a hard linear scale from it. So you have to think about like, are there diagrams that are sensitive to that? And there's some diagrams that sort of just aren't, and that's kind of in this hard region. Those ones are protected by RPI. You just get the C0. And then there's some diagrams that, this would be a diagram you'd write down in the SCT1, and it would just look like a normal subleading power term in the SCT1. Where does it go in the SCT2? And where it goes in the SCT2 is into this jet function, which is this loop. And then you match again. This soft becomes the same BS perp operator, except now with an extra momentum label specifying its plus momentum or its minus momentum. And it's going to be one of those from this side and one of those from this side. This will be the plus and this will be the minus.
And are there any subtleties with endpoint divergence in the Xi integral or the tilted Xi integral?
Oh, absolutely.
Okay.
That's the next talk.
Very good.
More questions? Okay, then let me ask one question. Actually, I have many of them, but I believe we will discuss it. So it's the same question which I asked you 1 year ago. So as you know, in our work, we have a lot of interesting contributions which come from momentums which go in opposite direction.
Yeah.
Do you have it or not?
Oh yeah, absolutely. The
So
Cassie here is not, doesn't have a, it goes from minus infinity. It's like, yeah.
Okay. So,
Yeah,
so
there's
you
no
see-
constraint. Like the thing that we've talked about in the past was sort of with Beneke's paper, and he put that constraint in. Yeah, there's no constraint in SCT on that variable. It's just an arbitrary label. And when you're thinking about jet physics, which is kind of what he was doing, then where everything's outgoing, then you have a constraint if it's going into
Yes,
a
that's
jet.
true.
But if you have an incoming proton, then yeah, you can have the gluon coming in or going out, same as you have.
Yeah,
Yeah.
okay, good. Are there more questions? Then thank you very much. I switch to the next talk. So next speaker is Anji Gao, which will continue with subleading power subtleties in CDs.
Yep. I guess it's working, yeah. Right. So I want to thank the organizers for giving me this opportunity to present our work here in collaboration with Johannes and Ian. So basically, I'm going to be continuing to discuss the subleading power TMD stuff, and in particular, I'll be talking about some soft subtleties, as Ian already mentioned. Yeah. So I'll give you some introductions and the motivation to study the subleading power TMD, and I will show two subtleties. The first one is that the repeat divergence can be both, including both multiplicative and additive term. Like the first one is the multiplicative, the usual leading power solve function, and the second term is additive. And the second subtlety is about the endpoint divergence, which is that this Cassie integral is divergent. So how we deal with that? Okay, so the introduction, yeah, as Ian already said, there are a few, lots of structure functions in the tensor decomposition of the Drell-Yan, and with different angular modulations. And in particular, all those azimuth asymmetric functions, they are the one that we are interested in. And let me give you one interesting motivation for why we are interested in this azimuth asymmetries, which is that it could potentially help us with the MW measurement. So basically, at the Large Hadron Collider, well, since you don't really measure the outgoing neutrino, we can only measure the outgoing lepton. And if you go back to this angular modulation, this W3, which has the cos phi angular modulation, which would basically shift the peak of this lepton distribution. So if there's no W3, then this Jacobian peak is exactly at the MW/2, but the W3 would make this a shift. So we need a theory input to realize compute this what the shift of this thing. So and in this limit, in the Jacobian peak, it's actually this Qt over Q going to small limit. So there are large logs that we want to resum. So it's very important to figure out how to do that. How to resum these logs. So to give you another motivation, it can improve the slicing method for the Qt subtraction for those observable that has the lepton PT dependence. So basically, if you go to higher and higher order in order alpha S, the power correction is going to be more and more important. So the numerical impact would be get worse at higher orders. So usually right now this sigma subtraction is the leading power resummation prediction, and if we can somehow predict more and more subleading terms in this delta sigma, we can basically improve our Monte Carlo calculation for the QT subtraction method. So I've talked about this improving the slicing method, and other motivation includes that we want to define some universal functions which can be used to both cities and drawing and other processes. And we want to make final predictions to incorporate the fixed order and a large log resummation. So now let's go to cities. There are also many angular modulation structural functions, and some of them are azimuthal asymmetric. And more motivation for cities, including that it's relevant for the future EIC, and although its subleading power is the effect can sometimes be large, and understanding these things will help us understand better about the 3D structure of hadrons and spin dependence and stuff like that. And this is also the motivation for universality of TMD functions and etc. So here is the review of the Baire factorization that Ian discussed. So this Baire factorization includes soft contribution, some kinematic contribution, p-perp contribution, and the most interesting one is this b-perp is the gluon quark-gluon-quark contribution, where this quark-gluon-quark correlator is defined here. This B is the collinear gluon field, has the energy fraction Kc. So the goal today is to understand how to renormalize this QGQ. So the first subtlety is the additive the additive divergence. So when you compute this QGQ in this Feynman diagram, here I draw this diagram such that the energy flow is from left to right. So we have outgoing gluon and incoming quark. So this Kc variable is negative, and if we calculate, we realize that is divergent, rapidity divergence. We use this eta regulator, so we get a delta Kc over eta divergence plus the L0, which is a plus function. So if we calculate the TMD fragmentation function, we also get a divergence. So we notice that there are these two divergences in the two collinear sectors, they cancel. But we want to define and this divergence was first noticed in this paper by people in the audience. So this is additive renormalization, additive divergence, because they cannot be cancelled by a multiplicative factor. But how to understand this? Well, let's go to example for the leading power. At leading power, this B, the beam function, if you calculate to one loop, you have a order of S divergence. And you calculate soft function, you also get divergence, but the product of these two are rapidly finite. So the lesson from this is that we can make use of the soft matrix element to cancel such divergence, and we want to add some soft matrix element to cancel such divergence. So in SET, we basically take the collinear gluon field to a soft gluon field, and in such way this rapid divergence is the same. So we can, in this procedure, this a QGQ is becoming a soft matrix element with a gluon in the soft matrix element. So by construction, such combination is rapidly finite, as drawn in this figure. This QGQ plus the leading power beam function times the soft matrix element is rapidly finite. So we define this red box object to be rapidly finite, and similarly we use the same procedure for the n-bar collinear side. So we know that this is 0, as Ian already discussed. So the sum of these two matrix, soft matrix element is 0, and we add a 0 to the previous factorization theorem, and we can replace the previous divergent QGQ by this new red not divergent QGQ. And right now each term is not repeat divergent. So a property of this control, let me just say that we find that this divergent, this part is just a derivative acting on the log of the leading power soft function. And due to the non-linear exponentiation for the soft function, we know that this derivative of log s has no double eta pole, and there's no epsilon pole due to this derivative. And from this, we obtain the zeta evolution equation, including an additive term and also the multiplicative term. So here we did some perturbative checks that this thing is indeed repeatedly finite. We check that there's no order eta square pole at the order alpha s level for the abelian channel and also the CFCA channel. So now let's move on to the endpoint divergence. So the endpoint divergence is that if you look at this formula, the Hall function, the subleading power Hall function is the C1 times the leading power C0, and the C1 has a log C in it. So remember that in the QGQ there's a 1 over Kc, which is L0, as I presented earlier. So it doesn't make sense to integrate this Kc. This integration is just divergent. So a natural question to ask is whether you can just put out the 1 over Kc to the Hall matching coefficient and define some plus distribution for the Hall coefficient, and then this problem there is no longer a problem because this thing can be integrated, but you still get some endpoint divergence because for other terms, because there's some log Kc over Kc in the order alpha s square in the QGQ correlator. If you calculate to the two loop QGQ correlator. So there's still some endpoint divergence. So the conclusion is that such endpoint divergence will appear irrespective of how you put this 1 over Kc to the C or the QGQ. So we need some refactorization theorem to understand the Kc going to zero limit. Yeah. So the answer is that this hard collinear contribution of the soft operator would exactly give you this refactorization theorem. So as Ian already introduced, this kind of contribution comes from when you match from the time order product of the this kind of contribution to the SCT2. So basically, such loops in the SCT1 is just the time order product of the next leading power Lagrangian insertion with the next leading power current. But in SCT2, this loop has a scale lambda q square, which is off shell, because in SCT2 it's lambda square q square being on shell, so lambda q square is off shell. So in SCT2 such diagram is in the operator. So this is some actual contribution different from SCT1 to SCT2. So such contribution start at the order alpha s squared. So this matching coefficient start at the order alpha s, because this is one loop, and the soft matrix element is also order alpha s. So although I didn't show the factorization formula for this contribution, well, Ian showed. But the basic, there are three terms. The first one is this matching coefficient, which can be calculated by these graphs. And there include the soft matrix element, which has the BS inserted in the soft matrix element, and with the PS hat, PS plus or minus being fixed by this PS hat. And also the collinear fields in this current would become a leading power TMD. So that's in this contribution. So then we just calculate each piece. This matching coefficient will give you, since these loops will give you some offsureness of PS Q to the power of epsilon, then it's actually exactly this will reproduce the log C in this formula. So basically, yeah, if you take the PS hat to be PS minus to be CQ, then this will reproduce the log C in the C1 Wilson coefficient. So the soft matrix element will reproduce the C to zero limit of the QGQ correlator. Basically, this soft matrix element will give you 1 over PS, and that's exactly the something in the QGQ correlator. So basically, we have this refactorization theorem. The C1 in this limit is reproduced by this purple term, and the B is reproduced by this orange SB over S term. So we just add this together. To be more specific, for Joyen, these two contribution vanishes because they add to 0, but we just write it down. It's an integral of this PS minus, and this is from the matching coefficient. This orange is from the soft matrix element. We put a C cut such that the lower cut contribution would cancel the divergence in the QGQ correlator, and the above cut contribution we just take it to be 0. So the consequence is that we use this formula to inside this bracket that everything is finite. So, but for the story for the cities is a little more complicated because there's an actual sign difference in these loops, in these two loops. So for this guy is a minus sign, and for this guy will give you a positive sign. So still we use the lower, we introduce a C cut and use the lower cut contribution to absorb the endpoint divergence in the QGQ, but the above contribution would actually give you something non-zero, which is what we call as a remainder term RCDs, and this is its formula. It's C1 convoluted with jet function, the difference of these two jet function, and also the soft function. So this since there is a new non-perturbative SB functions in this formula, we can find the new non-perturbative functions inside this RCDs. So using this perturbative calculation, we show that at the order of S square level, this is this formula for the RCDs. And this brings me to the summary. I show you that there is a additive rapid divergence in the QGQ correlator, and because of that, we obtained the zeta evolution, including both multiplicative and additive contribution. And there's also some endpoint divergence, which we use this hard collinear contribution to the BS operator to remove. And the normalization procedure for cities will leave behind the remainder term. So you may ask why do we bother to do all this stuff? Because we want to finally explore the RG and predict the logarithms in the next leading power structure functions. And with that, I want to thank you for your attention.
Thank you. So please ask questions. And let me, so we have plenty of time because we finished a bit earlier. I have several questions. So first of all, what I do not understand is why, could you maybe reformulate in different terms, why CDIS is so different from Drell-Yan? Because, say, naively, in some sense, I would say that factorization theorem as a statement about operators doesn't care of your hadron states. So, but here it appears that your operators knows about hadron states. How it happens?
Well, I guess it's just the soft term is always there, but in the Drell-Yan it's special because they are symmetric, so it cancels. So I would say
but
that.
If I would consider then, say, polarized Drell-Yan,
Yeah.
which is asymmetric.
Sorry?
If I would consider polarized Drell-Yan, which is asymmetric, will it cancel? Then it should also cancel the series. Could you repeat, sir?
This yellow thing is a vacuum matrix element, so it doesn't have to do with the hadronic state. And the thing that actually multiplies it in the end on the bottom there is BG. So those are just the leading power TMDs. So it's a vacuum matrix element of a subleading soft field strength insertion on your six-sided Wilson line. That's the yellow thing.
But isn't it the same for Drell-Yan?
It's the same object, but the Wilson coefficient that convolutes with it. So it's a function of some momentum fraction of that field strength that you inserted. And the Wilson coefficient has a theta, a theta that either makes positive or negative and picks out a different part of it.
Okay, well, I can imagine this. Okay. And second comment, so in our work, when we consider this additive repeated divergence, they actually appear more like what you call endpoint repeated divergence. Because we consider slightly different operator, which is, I think, derivative of your operator. Actually, our special repeated divergence appeared as, because the function is discontinuous at 0, basically we had the same 0. So, and that's why actually I thought that for this logarithm, which you solve here, will be also part of repeated divergence, but at next loop. Is it true or not?
No, we find it from the epsilon. Sorry. Yeah, we looked at the two-loop calculation. After the rapidity renormalization, you find this log from expanding in epsilon.
Okay, thank you. Are there more questions?
Okay, so this really from non-expert work on this. So you guys work on the subleading power correction. My question that I always thought that if you do after resummation, you get a pseudo form factor. So the question is that the pseudo form factor is the same as the leading power or not? I mean, for example, if you do CSS, right, you get ABC. Do you get the same ABC for subleading power correction terms or not?
You mean the double log?
Double log, single log.
It feels to me that double log looks the same, but the single log may not be the same. That's my impression.
May not. Okay.
No.
You're working. So you guys still working on this? Okay.
No, to my understanding, if we translate it to this ABC language, that would be same for next leading power. At next leading power, no one knows. Is it correct? Because Collins superkernel is the same.
That's right. So like the Collins superkernel is the same, so rapidity logs are the same. That sort of protects you in the double logs. But with the evolution in mu, it's a much more complicated story because what we find is that there's actually mixing between these various terms that he's talking about.
I may have another question. So looks like the C function would be different too, right?
Which C function?
ABC, Collins super, CSS.
If I remember, indeed, C function is what is the anomalous dimension for quark in Collins' case. That would be different, right? But we can check it term by term. So there is repeat evolution and ultraviolet evolution. Ultraviolet evolution will be different at next leading power. Repeat evolution is the same. Double lock is the same. So probably A and B is same and C is different, or vice versa. I don't remember.
Maybe two technical questions. So I know this, for example, you talk about cosine phi, and of course there's also cosine 2 phi. I was confused. I mean, of course, you can write down TMD from the quark-ground-quark correlator, but there's also so-called kinematic power correction. So kinematic power correction would be different, if I imagine, right?
Well, it seems to me kinematic correction is always associated with the leading power. It can be rewritten as some function of leading power stuff. So it's much simpler. I think it's very similar to the leading power story. Yeah. But the cos 2 phi that you mentioned is a leading power structure function. Cos phi is a subleading power, but cos 2 phi structure function is a leading power one.
This subleading power term too.
Sorry.
Subleading.
Oh yeah. That's another term. Yeah, that's a subleading.
Okay. Are there more questions? And thank you very much. So we continue our power correction session. Next speaker is Simona Radini. How to make it full screen? Let's see. A moment. You're welcome.
Thank you. Okay, so I will go over some of the concepts that you have already heard. I will try to kind of explain them from a different perspective. So you should see some similarities here and there in what I will talk about. So I will start with a very brief, kind of very empirical motivation why you would need next leading power, and not just stopping a leading power and call it a day for the next 20 years. Then I will kind of focus on new specific phenomena for next leading power, because if you study your factorization theorem, you will find a lot of similarities to leading power and some different kind of features, new features. And so the similarities I will skip. I will focus only on the new stuff. And here, kind of overview. So you will get complex coefficient functions and complex TMDs. So they will no longer be just real objects. And this you can relate to what you already heard a little bit. And also I will talk about the special repeated divergences, which, again, you already heard. So I will try to be more specific. So this is a picture that you can find in different phenomenological extraction of TMDs of leading power. And okay, specifics may vary between different works and different time frames, but kind of the main underlying idea is that if you study your chi-square of your fit, depending on the Qt over Q ratio, at some point you see a sharp increase in your chi-square if Qt over Q becomes too large. So most of phenomenological studies quote this kind of 0.25, 0.2, depends on which papers you choose to read, but the main underlying idea is the same. You have a cut in Qt over Q, and if you want to go above, you need to include some type of power corrections. So, okay, question why you would want to go above. The main motivation is that you have data above this point, and you would like to include as many data as possible, because otherwise you're missing out to what experimentalists already did. So, at the leading power factorization, the main idea is that you drop the masses of proton and hadron to study the factorization theorem. You ignore basically correction of the order of Qt over Q, where Qt is the transverse momentum of the probe, and Kt over Q, where Kt is the transverse momentum of the partons that enters your TMD description. And also you ignore say, pure quantum effects in which you have not just quark TMDs, which is standard leading power, but you also have this type of quark-gluon-quark stuff. So how do you extend kind of conceptually this to next leading power? Of course, it's not unique depending on what type of corrections you want to study in next leading power. You can do, you can choose to study, for example, just the kinematic type of correction, the KT over Q. So we did it at 3 level and 1 loop, and Alexei did it for kind of the complete tower of kinematic corrections for CD. So you can study those type of corrections. In principle, you could study, for example, mass corrections. But okay, we didn't touch mass correction, so in our approach to next leading power factorization, the masses of the atoms are still 0. So we focused basically on the first term in kinematic corrections and in the first type of genuine corrections, where genuine refers to the fact that in your description, it will enter a new type of operators. In this case, it is quark-gluon-quark. It is next to the leading type of behavior. So the main idea of what I want to stress today is that once you go beyond leading power, you cannot assume that your partons have strictly positive momenta, longitudinal momenta, that is. That is because if you study leading power factorization, since you have just basically quark scattering and nothing else, it is in some sense semi-classical in picture, and you can always assume, you just have to change sign somewhere, but you can always assume that partons do not carry vanishing longitudinal momentum, because vanishing longitudinal momentum would refer to one physical point in the cross-section. So since you cannot reach a physical point, you don't care about partons with 0 momenta. The problem is that at next to leading power, it starts to happen that you can reach points in which one parton has 0 longitudinal momentum, because that specific parton will not be probed exactly by the external probe, but a combination of that parton and something else. The combination will have physical momentum, but the single parton can have vanishing momentum. And this generates new phenomena. So we focus on CDs, next to leading power, next to leading order. And the first observation is that historical works wrote the 3-level cross-section in terms of kind of generic twist tree distribution, so in standard lingo, one good component of the field, one bad component of the field. So 2 field operators, but one with kind of a bad component. It turns out that these type of operators are not very good to study beyond 3 level, because they do not have autonomous evolution, so they have evolution that is a mess. And what happens is that if you study evolution of these operators, you naturally identify two different types of sub-operators in which you want to classify your cross-section with. One is basically, you can think of it as derivative as twist 2 operators, and the other is this new type of genuine operators in which you have quark-gluon-quark. This is due to basically quark equation of motion, in which you have kind of standard transverse derivative plus the field part. Then another kind of observation is that next to leading power, next to leading order, because you generate this type of transverse derivatives of leading twist operator, you need in some way to restore kind of boost invariance / reparametrization invariance in your rapidity scales, because the transverse derivative will probe the ratio of your rapidity scales for the first hadron and second hadron. So you need some method, something in the cross-section must happen such a way that this ratio is, you're not sensible to the ratio. And then I will the main idea is that you get these new effects when the gluon momentum goes to 0. So in your quark-gluon-quark correlators, your gluon momentum goes to 0, you get these type of new effects. So first phenomena is complex coefficient functions. This happens already at leading order, so kind of alpha s to the 0. This is important. This is kind of fundamental, kind of conceptually. It gives you, say, two-Sterman-like contribution, so a quark-gluon-quark correlator in which the gluon has 0 longitudinal momentum. And you will actually be able, at the end I will say a few words, but you will actually be able to kind of see the connection to the actual two-Sterman function. And so said like this, you can ask why this happens. I mean, maybe you did a mistake. So the point is that if you study this type of quark-gluon-quark correlators, of course, for CDs, it is product of electromagnetic currents. So the gluon is radiated by a diagram as the one that you saw in the picture. This is, of course, tree-level diagram, in the sense you do not have loops anywhere. This is just production, external production of one gluon at tree level. The problem is that if you write these diagrams in whatever, if you use CAT, QCD, whatever, this is a field of gluon. It's not field strength tensor. But of course, this a field is not what you want. I mean, that has bad gauge transformation properties. So what you really want is the gluon field strength tensor. And to do that, of course, you know, F mu plus is just the derivative of the, if you choose your gauge carefully, it's just basically transverse, kind of light cone derivative of your transverse field. If you invert the light cone derivatives, you get an integral. And if you think about Fourier transforming this stuff to momentum space, you see that the integral of a phase is basically just 1 over x gluon, plus or minus I0. The plus or minus I0 depends on the process that you're actually studying, because you have to ensure good analytic properties of your functions, and those depends on the process that you're studying. And of course, this is kind of very well-known type of distribution. This factorizing into principal value plus delta function. Principal value is what you would normally use, just 1 over x gluon and forget about it. The problem is that if x gluon goes to 0, in this case it can, you pick up also the delta contributions. And these delta contributions, of course, comes with imaginary unit, and these participate to the coefficient function for your process, basically with an imaginary part. This is, of course, kind of, it can worry you, because cross-sections are real. So you do not want this spurious kind of imaginary unit floating around and breaking everything up. So you need something that cures it. And the first hope, maybe it is that, okay, maybe it is some weird effect, but it basically completely decouples from everything else. It lives in its own world, so you can do something about it. But this is not the case, because this x equal to 0 point, it turns out, if you study your evolution equations for your operator, is not a fixed point for your evolution equation. So if it would have happened that x gluon equal to 0 would have had autonomous kernel, so it would evolve by itself, and everything else was in another sector and nothing took to it, then it was good. You could have just kind of take it out. But it is not stable under evolution, so this is a very graphical representation of what evolution of this object does, what evolution does to these objects. Basically, if you start saying in a point in which x2, which is x of the glue, is equal to 0, evolution will move you around, for example, this diagonal or kind of parallel to the axis. Of course, if you move parallel to x1, this is kind of, it will stay on x2 equal to 0, so it would be good. But the problem is that you have this type of evolutions in which it moves basically diagonally in this project-out plane, and therefore it goes outside x2 equal to 0. So you cannot cure it. Okay, this also kind of minor remark. This happens for all Maxwellian power coefficient functions. It is not like it is isolated in one very specific piece that maybe it has something to do with spin structures. That no, it is kind of general presence in general. And also kind of side remarks. If you study TMD fragmentation functions, because you have if you put 0 momentum for fragmentation, you get basically 0. This effect is only present for TMD PDFs. So also this also tells you that it cannot be some kind of compensation between PDF and fragmentation function for cities that happens. So it has to be something else. And this brings me to the new phenomenon number 2, is that naturally it comes out that you have complex transfer momentum distributions. It is no longer true that as in leading power that you have real transfer momentum distributions. Here you get complex objects, so something with a real part and imaginary part. And if you get complex objects, you want an interpretation for this. This is more complicated than just leading power. And what you can do is after looking at the equation a little bit and thinking a little bit, is that these Maxwellian power TMDs are basically emission of quark and absorption of quark gluon, or some combination of this. And so of course, you have a complex object. This is quantum mechanics. You have the amplitude and the complex conjugate of the amplitude. In this case, amplitude and complex conjugate are not the same physical platonic process. One is just emission of quark, the other is absorption of quark gluon. So you basically, you can, and it turns out that from the point of view of equations, it is natural to study these in terms of real and imaginary part of these TMDs, and you can relate them to physical interpretation as the real and imaginary part of this interference process, which is very neat. And of course, this on your left is for TMD PDFs, in which you have incoming proton and emission of something plus inclusive everything else. You have the same kind of idea for fragmentation, in which is slightly different in the sense that you have incoming quark that fragments into your hadron and everything else. And in the other side, you have coherently that the quark-gluon pair produce the hadron and everything else. So this is kind of, say, physical interpretation for your complex TMDs. And you may ask also, okay, you have these kind of effects, how important they are, so how much they weight in the cross-section. Because if it turns out to be very small, then you would not basically care at all and live your life happily. So, okay, of course, we do not have any extractions of this, so we cannot give you a numbers or whatever ratio to leading power or anything. But you can get some vague idea on the behavior of your TMDs if you match them at small transverse separation or kind of integrate basically the transverse momentum of the parton to get your collinear functions. It turns out that some of them, okay, first of all, you have a lot of TMDs at this next leading power. They're basically 32. Turns out that only 16 of them can participate to CDs or Drellian cross-section. So basically, effectively, for CDs and next leading power, we have 16 new type of genuine contributions. Compared to the table that you already saw for leading power, they are just 8. So here already you double the number. So in total, you will have 16 plus 8 distributions. And small b matching also help you kind of reduce this number. So if you study it at 3 level, which is kind of more or less the state of the art, plus there is something known that for some pieces, it is known the singular parts because like 1/b squared, one loop. So if you combine this information, you get basically 8 out of the 16 that has non-zero matching. Of course, more of them, we don't know how many at the moment, will receive matching starting from one loop. So if you do the matching at one loop order, you will get more contributions, and more of these TMDs will kind of appear, but you can think, okay, they start the next leading order, so maybe it is not so fundamental to think about them right now. And to get an idea, you take one of the structural functions for CDs. We already heard a little bit about this, so take the UU cos phi, just because you have unpolarized everything, so it is simpler to study. And you look specifically for these terms which have vanishing gluon momentum fractions. And for those, I can give you expressions. They're not very instructive to look at the moment. So you should trust me on this if you want. Otherwise, you go and read the papers, and there are all the details that you may want. If you look at this, you basically see that they go like this specific twist strip PDF, which happens to be also the one that participates in the matching for the Sievers function, so the just term. So besides the correction M over Q, which is present because of the next leading power nature of this object, you get basically the quote-unquote the same non-perturbative content. And another small observation is that in this, the participation of this just thermal contribution, this cos phi structure function, is actually enhanced by the Bessel convolution that happens in the TMD cross section. So it is, you could say that it is more or less of the order of this cos 2 phi object. If you look just at this just thermal piece, of course, then you have all of the other stuff. This is to say that if you believe that F UU cos 2 phi, it has an important and fundamental non-perturbative contribution, then you are forced also to think that FUU cos phi has an important non-perturbative contribution. FUU cos phi, though, is not a leading power structure function. It is of next to leading power. So, conceptually, if you think that FUU cos 2 phi is important to study, you should also think that FUU cos phi is important to study. Okay, so I already mentioned a little bit about this matching stuff. It turns out also that is quite, you get quite complicated expressions for this matching if you go, if you include mass corrections or, I don't know. So, thank you. Kind of last conceptual point, I already kind of foreshadowed it a little bit, is this special repeated divergences. You already heard in the talk of Angie Gao about this. So let me just kind of reformulate in our language a little bit. This happens when you when you take your here it's your quark-gluon quark. So standard rapidity divergences, in the way in which at least we isolate them from the TMD operator, is that is through loops like this. So here, it's, for example, is your quark. This is the gluon. You should read as quark-gluon quark operator. And rapidity divergence happens when you connect one sector to the other at the, say, to the Wilson line, and then you, in position space, you take this point and you send to infinity. And this generates your rapidity divergences. So in your quark-gluon, if you have just quark-quark case, it is basically just one diagram. You just remove this gluon and those basically generates your rapidity divergences. In this case, you have a bit kind of basically two diagrams, because this is attached to Wilson line, and that you can do nothing about it because it is what generates rapidity divergences. But you can attach either to the quark or to the gluon, so you get basically two, and then you have the diagram for the other sector. So you get basically three. It's not too bad. But then you have conceptually different type of diagrams, because instead of attaching to Wilson line, you attach to the gluon operator that is inside your TMD. And this basically kind of perturbatively, this basically annihilates your gluon operator, and what you're left on the outside is just quark-quark operator. So basically leading power TMDs. This of course, if you keep fixed this point, this is just finite. It doesn't generate anything weird rapidity-wise. But if you take this point then and you send to infinity, this generates rapidity-style divergences. And this, you may ask, well, maybe it doesn't happen. But if you remember a few slides ago, I told you that QFQ as a correlator enters in your cross-section via an integral, and that integral has infinite lower bound. So it happens in your cross-section that this point goes to infinity. So you generate these special rapidity divergences, and you may say, okay, this is another very unwanted thing in your cross-section. So first observation, it turns out that if you do it correctly and you sum all the terms, these special rapidity divergences actually cancel in between terms. So your cross-section is finite. You can check this. The point is that they leave behind not kind of the divergence cancel, and they leave behind something. And this something is important to exactly remove the dependence over your ratio of, okay, here is written with the square roots, whatever, for your rapidity scale zeta and zeta bar. Factorization theorem fixes the product of these objects. So it tells you that if you work out your factorization theorem, it tells you that zeta zeta bar should be this particular combination of q square and qt. The problem is that it tells you absolutely nothing about what zeta over zeta bar should be. So you are completely free in this choice. You can choose zeta over zeta bar 1, 2, 20, 0.1, whatever. And it must not change the result. If you do it at leading power factorization, you can see it, and nothing changes. You can change the ratio, and you're good. And next to leading power, because you have this kind of okay, here is missing an L and for next to leading power. And next to leading power, you get this type of this is basically, if you Fourier transform, this is KT. So this is kind of kinematic power corrections. This transverse derivative will give you sensibility to these type of scales, exactly via this type of kind of derivative of Collins superkernel times this log, if you combine everything. Importantly, this must not, I mean, this dependence must cancel. So what happens is that these special rapid divergences, they exactly leave behind this type of object. So basically what happens is that if you include special rapid divergences everywhere, you see your transverse derivative, you replace with transverse derivative minus transverse derivative of Collins superkernel times this very specific type of log. And, and this basically restore your reparametrization invariance under zeta and zeta bar. So, okay, just, I leave basically the important points. I finished. Thank you very much.
Thank you very much. Other questions?
Yeah, I have a question about these terms that remain after you subtract rapidity divergences, so these logarithms of zeta and zeta bar.
Mm-hmm.
At leading order in your paper, you find just basically a logarithm of the ratio between the delta plus and delta minus, right? Some combination of this. And this translates to the ratio of zeta and zeta bar, if I'm correct.
Yes. Yes.
Yeah, but at next to leading order, you will also run into logarithm squared of delta plus and logarithm squared of delta minus because of the convolution with the hard function.
Yeah, so that the point is of this subtraction of special rapid divergences, maybe Alexei knows more, but I don't know if a next kind of next to leading order, so the next step, they will still cancel. Like it has to be proven. Now we proved that this order everything works fine. You can do probably so you can check.
Referring to the previous talk, previous speaker told us that they may not cancel because we have extra endpoint divergence. I don't know. I didn't check it by myself.
Thank you.
So, are there more questions? So, I don't have any questions. It was perfect talk. Thank you. So right now we have a coffee break for half an hour.
Thank you. So yeah, we have coffee break. Thanks for about 30 minutes. Coffee break is served just in front, in this room in front. And oops, you can leave your things here. We have a person which is looking after your things, if you wish to. And okay, we reconvene at 4 p.m. Thank you.
Let us start our second part of next leading power session, and the first talk by Max Jaschma about studying of next leading power effects with jets.
Okay, good afternoon everyone. Welcome to my talk. I will be talking about next to leading power effects in transverse momentum measurements with jets. This talk is based on the V2 of a paper that we posted on the archive today. The reason for a V2 will become clear later. So, what to expect from this talk? So the main result of this talk will be a factorization theorem for die-jet production that holds up to next to leading power. Now, why would we study this? So, next to leading power can give you more theoretical precision for making predictions at colliders. So that's one reason. Another reason is that at next to leading power you get a new phenomenon that manifests itself as azimuthal asymmetries. So that is something really a next to leading power effect that you can directly observe. But then another question might be, why do this with jets? And there's multiple reasons for that. So one reason is that jets really provide a nice playground for theorists, because jets, believe it or not, are simpler than individual hadrons. And another reason for doing this is that if you choose the right jets, you can calculate all your predictions in perturbation theory. So that's really nice. Under some assumptions, of course. Another motivation is the upcoming electron-ion collider, wherein semi-inclusive deep inelastic scattering, you can really get high precision measurements of the cross-section, and their next to leading power effects will be really quite important. So the outline of this talk is as follows. It's split up into two parts. In the first part, I'll discuss the method we use, and I'll discuss how we get to our factorization theorem. And the second part is basically the reason that we had to put up a V2, and it has to do with rapidity divergences and endpoint divergences, and I discuss the solution that we've come up with. And I'll end with a conclusion and outlook. So let's dive in. So the process that we consider is E plus E minus going to two jets. And the outgoing jets in this picture are not necessarily back-to-back. That can be for several reasons. And we will study jets that have a recall-free jet definition and also a large radius. And I'll discuss that in more detail soon. So deriving the factorization is actually easier in the back-to-back frame because there's some simplifications, and in this frame the incoming electrons are not back-to-back, and this introduces some transverse momentum for your photon in that frame, and that's what we will do the power expansion in. So, as I've said, you have some freedom in how to define your jet. You can choose a definition for a jet axis, and you're free to decide which particles go into your jet and which do not. So what we do is we choose large radius jets, such that all the energetic radiation that comes out will be clustered into one of the two jets, and it will simplify our analysis, as we see later. And also, choosing them to be recall-free allows you to simplify some things, because then the jet axis is not affected by additional soft emissions. So, more about our jets. We have some jet algorithm or some recombination scheme to combine the momenta of multiple particles to form the jet. And these are some of the definitions that we use. As you can see, it's not simply adding up the momenta of the particles, because then you would be sensitive to additional soft radiation. So instead, what we do is we provide some weight to each particle, and that weight is going to be the energy of that particle. So the more energetic a particle is, the more that's going to dominate in which direction your jet axis is. And for the winner-take-all scheme, the direction of the jet momentum is simply the direction of the most energetic particle in your jet. All right, so let's go to the cross-section. So what do we actually measure? We measure some angle related to the jet and lepton plane. And we also measure the transverse momentum of the intermediate photon. And connected to that is also some azimuthal angle. And the cross-section
can then be separated into a leptonic tensor and a hadronic tensor. And the hadronic tensor, that's going to be the main focus from now on, because that's actually the one unknown piece in this cross-section. So what is our goal? We want to obtain some expression for the hadronic tensor in terms of some hard functions and jet functions and some Lorentz structure in front of it, and we want it to hold up to next to leading power. And additionally, we want that each term in this sum is finite by itself. So to derive factorization, we've used background field methods. For those who don't know, let me discuss some of the basics of this theory. So it's based on the observation that your external states, the particles that come in your detector, is dominated by collinear and anticollinear particles, which have a momentum that scale like this, in the usual light cone coordinates. Now, the idea of the background field approach is to split the full QCD field into some of different fields, so that both the collinear and the anticollinear particles get their own fields. And what you can then do is you can derive some power counting for the different fields. You expand your Lagrangian, your action, and then you can integrate out all the dynamical fields. So to get to this factorization, we've done it in 5 steps. So the first step is to expand the current up to next to leading power. And the second step is then to derive what matrix elements you get. In the third step, you take these matrix elements, you apply some discrete symmetries to get your jet functions. And then in the fourth step, you derive some evolution equations for your jet functions. And in the final step, you combine your results to get the hadronic tensor and the cross-section. So for the first step, you write down what the full current would be, and then you integrate out all the fields that are not collinear or anticollinear. And the results can be seen in the second equation that holds up to next to leading power. Note that this is just the leading order expression. At higher orders, you get some matching coefficients in front of these different terms as well. So the second step is then to go to the hadronic tensor and to factorize the matrix elements. And so at leading power or next leading power, the action separates into several pieces. And specifically the collinear and anticollinear fields, they don't interact with each other, which allows you to separate these matrix elements as follows. From here, it's just a matter of doing the bookkeeping, so you have some Fierce relations that you need to apply, and you need to do your Lorentz decomposition. And once you have all the matrix elements that contribute to your hadronic tensor, you define your jet functions. And this is where some nice properties of jets come in, because jets are really much simpler than hadrons. For example, they are symmetric under charge and parity conjugation, as opposed to the proton, for example. And also, the jet measurement is spin independent, so you don't get all these different spin structures that contribute. Now, here is where our nice jets come in, because we choose jets with a very large radius, and that means all energetic particles go into the jet, and therefore we lose a momentum fraction in this analysis, because the momentum fraction will simply be 1. Now, also, as I've mentioned before, we have a recoil-free jet axis, and so soft emissions will not affect the jet anymore. Now, we find 3 types of jet functions, of which 2 are independent. So the first one is simply the jet function you find at leading power, defined in terms of the familiar Xi field, or chi field in SCAT. And at next to leading power, you also find a kinematic correction, which is simply a transverse derivative of this quark field. And at next to leading power, you also find a higher twist contribution. And this is where the quark-gluon quark correlators that have been discussed before come in. And you should note that this involves an additional momentum fraction, because you now have a gluon. Now, we have the matrix elements ready, but of course, staring at matrix elements is not going to be interesting. Instead, I'll show a picture of what this looks like. So this is a picture you can draw for your higher twist correction, which involves an additional gluon field. And as you can see on the left there, That's the correction to the current, so an additional gluon is produced, which you assign a momentum fraction xi. And then when you go to your jets, you see that there's an additional gluon field in your jet, leading to the quark-gluon-quark correlators discussed before. And this is the type of picture you get. Now, the next step is to write down the evolution equations. You need these evolution equations if you want to do resummation. And eventually we want to do that, of course. Now, the evolution equations for the leading power jet function and also this derivative, this transverse derivative of the jet function, it's well known. But for the higher twist one, it's been derived more recently by several independent works. And for our case, it can be written as a nice convolution in this additional momentum fraction xi. So this is the final step, to go to your hadronic tensor and combine all the things, and this is the results that you get. And I'll go over the several terms in more detail. So this is the full cross-section that you get, expressed in terms of the jet functions, and I'd like to go over the terms one by one. So this is the leading power term. It's just a very simple product of two jet functions and some kinematical prefactor. Then also, this is next to leading power, so there is a kinematic correction to this prefactor, or basically this kinematic prefactor also has a power expansion. Then we get this kinematical correction, which involves a derivative of the leading power jet functions. And notice that it actually has the same prefactor as the one before. And the higher twist distribution also appears, so this has the additional convolution in the momentum fraction xi, and that will come back later. But I want to look at this expression one last time, because as you can see, all these kinematical prefactors for the next to leading power jet functions, they're the same. And so experimentally, you will not be able to distinguish between the different next to leading power contributions, at least for the E plus E minus to 2 jets case. Now, another thing you should note is that all these next to leading power jet functions appear in a very particular combination, namely as the difference between the two collinear sectors. So that means if you use the same jet definition for both of your jets, then actually all this next to leading power stuff is going to cancel out. So in order to get a non-vanishing result, you need to take two different jet algorithms for the both jets. So let's summarize part one so far. We've derived a factorization theorem for E plus E minus to 2 jets. We used the background field method for expanding the current. And we found that at next to leading power, there's only 2 independent jet functions. And we found that all contributions of these new jet functions vanish if you have the same jet algorithms. So now let's go into part 2 of this talk, the subtleties. So one subtlety that you get is rapidity divergences. Now, at leading power, we also have rapidity divergences, and they come from the vague borders between your different regions. So this is the usual picture that you get for rapidity divergences. Now, these cancel via the soft function, or in the background field method, this would be an overlap factor. And for this specific regulator, but also for other regulators, it can be shown that you can split this soft factor into 2 pieces and then absorb each of those 2 pieces into the jet functions. Doing this will cancel the rapidity divergences, but it does introduce a new scale, a rapidity scale. Now, at next to leading power, not all rapidity divergences cancel after you've done this procedure. Special rapidity divergences remain, but they cancel between the collinear and anticollinear sector because they only appear in this difference, and it can be shown that the divergences that they get are the same, so they cancel in this difference. Now, let's discuss endpoint divergences. So in the TMD operator expansion literature, these are also called special rapidity divergences. But really, no matter the language, they come from this convolution with this additional momentum fraction. So where do they come from? They come from the convolution with this hard function and this twist tree jet function. And in the limit that psi goes to 0, you get some ugly divergences like this. And these are ill-defined. And so now we want to make sure that these drop out of the cross-section. So, how to do this? What we want to do is we want to subtract this singular behavior of the jet functions, and then we hope that this cancels out. Now, to subtract this, we realize that this twist tree jet function describes a jet that is initiated by a quark-gluon pair, where this psi is the momentum fraction of the gluon. Now, psi to 0 is the problem, but that limit exactly corresponds to this initiating gluon becoming soft. So, what we came up with, inspired by Stuart and his collaborators, we found that this limit of psi to 0 can be captured by a next to leading power soft factor. And we have a matrix element definition for the soft factor as well. And the key point is that the same soft factor appears for both the collinear and anticollinear direction. And so the singular behavior as psi goes to 0 drops out when you take this difference. And so you can subtract the singular behavior and use the same jet functions. There is one subtlety, and that's the rapidity regulators that you have in your soft factor. Because in principle, the collinear and the anticollinear sectors, they can have independent rapidity regulators. Now, a problem that you run into is when you go to higher orders. Because at higher orders, your hard function has a logarithm in this psi, and your next to leading power soft factors, they have this simple behavior here, but as you can see, they have different rapidity regulators. And if you work out what this type of integral would result in, it results in some logarithm squared. Now, this is only finite, and in fact 0, if these two regulators are related. Otherwise, if they do not obey this expression, you will get a divergent result. And so the subtraction terms do not cancel if you do not take this. So this is the approach that is roughly used in SCAT. And in the background field method, a slightly different approach is used. So what they do is they have a slightly different notation. Instead of psi, they use x2, but it's, there's a relationship between the two. But what they define is they find some physical twist tree distribution by taking the distribution that contains a singular behavior and subtracting some term that involves a convolution of some perturbative kernel and your leading power jet functions. So the way this kernel is constructed is you calculate this convolution between the hard function and the twist tree distribution, and then you demand that it is finite, and that's the way you construct your kernel. And that's done order by order in perturbation theory, and then you cancel the subtraction terms. So let's compare the different methods there are. So in SCAT you have an explicit soft mode, and that allows you to introduce a next to leading power soft factor. Well, in the background field method, this soft mode is not there. So in the background field method, as I've said, you define a physical distribution with some perturbative kernel as a subtraction term. Well, in SCAT, you use a next to leading power soft factor to do this. Now, in SCAT, doing this with a next to leading power soft factor guarantees that your subtraction works to all orders in the strong coupling. And for the background field approach, you have to do this order by order in alpha S. But in SCAT, or at least what we found, is that to do this to all orders, your rapidity regulators need to be related to each other. Otherwise, you still have divergences that remain. While in the background field approach, it's only been worked out to leading order what this subtraction term should be. But we think if they extend this to higher orders, they will find, in fact, this constraint that rapidity regulators need to be related. In summary, these two approaches, they exactly agree on the bare matrix elements that appear, but there are some differences in how they treat the subtraction and cancellation of the divergences. Now, we're ready for some results. So we've calculated, and others have calculated, all the ingredients that are needed to do leading logarithmic resummation. So the anomalous dimensions, they have been calculated. The hard functions have been calculated. Those for the twist tree have been calculated up to NLO by Alexei, for example. And what we've done is we've calculated our jet functions for different recombination schemes. And we've also calculated this next to leading power soft factor that is needed for the subtraction. And in this plot here, you can see what our jet functions as a function of xi look like for different jet algorithms or different recombination schemes. But the key point is that we have all ingredients at order alpha s. So in principle, everything for leading logarithmic resummation is available. So with that, I'd like to go to my conclusions. So we've achieved factorization at next to leading power, where we've expressed the cross-section in terms of hard function and jet functions, and each ingredient is finite and regular by itself. So what to take away from this talk? The behavior of xi to 0 can be subtracted and cancels in the cross-section, at least for our case. And we've done this using a soft mode. And so even though it cancels, it might be useful to have a soft mode available at next to leading power. What's next? So we still like to verify if all this works at order alpha s squared, because there's some subtleties that we could run into. And of course, what we want to do next is resummation, because we have all the ingredients available, and so we should look into that. Also, keeping in mind that the EIC will be coming, we want to extend this analysis to semi-inclusive deep inelastic scattering, specifically to see if we can probe the twist tree TMDs for hadrons using our jets. And with that, I'd like to thank you for your attention.
Thank you for the talk. Do we have questions?
Hi, very nice talk.
Thanks.
I have maybe it's a naive question, but what I get from this is that when you go to next leading power, you have, for instance, to modify to add another contribution for the jet function, which is your J21, right?
Yeah.
And then at the very end, you encounter troubles in dealing with the rapidity divergences, right? Which has to do with soft sector. So my question is, if you just do power counting, there are more than just more contribution than just modifying the collinear sector. So the soft sector in that case, the soft factor, has different and other terms, which I think I didn't see in any of the talks talking about the next leading power correction. So my question is, once one include those corrections at the next leading power, which are there, do this problem with the rapid divergence is naturally fixes by itself, or you still have to set the two regulator equal to, I mean, to some kind of artificial or an ad hoc or by hand modification on the formalism? So
yeah,
that's the
I
question.
think I understand your question. So does this additional soft factor that you talked about, is that the same as the one that appeared in Angie's talk, or is it something entirely different?
It's very, so for instance, you can have a quark line. So leading power, you just have quark lines connecting the hard with the collinear, one jet, and the same on the other side.
Yeah.
And then you connect the two jets with the R part with as many scalar polarized gluons as you want, and you can connect those collinear parts with the soft factor there with as many collinear gluons as you want. But in principle, you can have a quark line that goes to the jet, then goes to the soft, goes to the other jet, and come back to the R part again. And that is a next leading power correction, which is not, I mean, it's 1 over Q square, it's 1 over Q square more than the leading power. that, for instance, or for instance, a gluon, a physical gluon connecting the hard.
I think
to
then
the soft.
in that sense, it may be what we would consider next to leading power.
Is
because
that
it's
next?
yeah, because for us, the next to leading power means a 1 over Q suppression, or specifically QT over Q suppression. So everything that's suppressed by 2 factors of Q, so Q squared, that's what we consider next to leading power.
Ah, okay. Okay, thank you.
Are there more questions?
Yeah, with jets, you kind of get rid of the fragmentation part, so you have just the distribution, right? So there are these 2 kind of higher twist versions of sieverts, which appear in the either beam or target sinusoidal modulations. I don't see why you cannot measure them. For sure we can.
Yeah, so for the sieverts, if I'm correct, that includes some non-trivial Dirac structure, right? Or is this a different function?
It is, I think the generic name of those functions is like, one is G-perp, another is FL-perp.
Yeah, so for us, they vanish because of the symmetries of the jet. So for hadrons and for fragmentation functions where you measure, for example, a single hadron, these contribute, but because for us, all particles enter the jet, and with that, a certain symmetry.
I'm not sure symmetry will kill those. You will, this asymmetry is sitting in the distribution. It doesn't matter what happens in the fragmentation part, so it should be there.
Okay, then
maybe we can look in details.
I think it might be contained in here, but it's hidden.
Or we are talking about different things. That is also possible. But those 2 functions for sure should appear in the final asymmetries for jets.
So you mean transverse and longitudinal photon function?
No. If we are talking about the same twist 3 TMDs, then you have 2 TMDs, twist 3. One appears in the when you have a longitudinally polarized beam unpolarized target, sinusoidal modulation. The other one in the longitudinally polarized target, unpolarized beam. Both are sinusoidal modulations related to these 2 kind of higher twist versions of sieverts.
So, okay, one thing I did not discuss, we consider unpolarized incoming beams. So we use the leptonic tensor without the polarization.
So you have unpolarized target and unpolarized beam.
Yes.
Oh, okay, that's the difference. Then, but you can do the same for polarized,
In
right?
principle, you can. Yeah. Then you might indeed get additional structures appearing. Yeah.
Yeah. Okay, you have already answered. In principle, we can do what you are asking. Just we had to start from somewhere. So we started from the case where everything was unpolarized, and then see what kind of asymmetry are coming out. But in principle, one of our targets is actually to point to the case of the sieverts in the initial state and the jet in the final state. So if you do this, what kind of jet do you get? And the jet that we present here are one possible answer to that. So when you compute total cross-section, there are contribution to asymmetry coming from higher twist jet that can arise there, probably. But we have to study them.
Jets.
No, they're not polarized jet. They are this kind of jet. But
that kind of actually polarized jets, I think.
Okay,
so
we
are
keep
there
it
more
for
questions? And let me allow for one short question for myself. Somewhere, I think it was page 20 or something like that. Not so fast, I cannot trace it. Yeah,
With the evolution?
A bit later. 1 second. Where you start to talk about repeated divergences.
That's indeed quite a bit later.
A bit later. And a bit more later. Okay. When I just you had a formula. I just don't remember precisely which. But your derivative of leading twist TMD is also repeated divergent. So what is the fate of this repeated divergence?
That one.
Because we discussed everything for twist 3, but what happens with this guy?
I think you mean this, right? This
one, exactly. Yes.
Yeah, so these indeed cancel between the collinear and anticollinear, and they result in the derivative of the Collins-Soper kernel. So what you can do is So how you get this one is you first take the derivative of the leading power jet function, and only after that you divide by the square root of the soft factor. And because of that, you get this divergence. Now, if you would have simply taken the derivative of your leading power jet function after the subtraction, that would have given something finite. But of course the two differ, because for the one you first divide by the soft factor and then take the derivative, or for the other you do the other way around. And if you work out the difference, that's going to be a derivative of your soft function. So we can look at this in more detail, but you get a derivative of your soft function, and then in this combination, and using the exponentiation of the soft function, you can see that you get a derivative of the Koldin-Soper kernel, if you work this out.
Okay, thank you. Okay, then, thank you very much. We go to the next speaker. 1 second. No? So, our next speaker is Anya Venkata. So, please, talk.
Hello? Yeah. Okay, so what I'm about to say is a little tangential to TMDs, but hopefully it's useful to some people in the audience. What I'm going to be talking about is fully inclusive observables in time-ordered perturbation theory. So there are a few motivations to study time-ordered perturbation theory. So one question you could ask is, if you're doing a fixed order calculation, can you do it numerically with Monte Carlo, right? The second question that you can ask is that you so when you normally do it using your ordinary covariant perturbation theory, you encounter all sorts of singularities. And is it possible to avoid these singularities by a reorganization of perturbation theory? So this is a question. This is one question you could ask. Another question you could ask is, does time-ordered perturbation theory know about power corrections? Right? There's famously people think this. For example, the only proof of Glauber decoupling that I know is through time-ordered or light-coordinate perturbation theory. So the other question that you could ask is, can you make contour deformations to manifest finiteness in a fixed order calculation? And hopefully I can answer some of these questions in this talk. So so I'm going to start by reviewing time-ordered perturbation theory, and then I will hopefully say some things about how to organize time-ordered perturbation theory to manifest only the to manifest finiteness at a cross-section level. So time-ordered perturbation theory is an alternative formulation to ordinary perturbation theory. It's older, it has more terms, but it has fewer singularities, and this is sort of why it sort of knows about power corrections and so on and so forth. So what are the rules of time-ordered perturbation theory? The rules, so I'll explain these rules since not everyone is familiar with time-ordered perturbation theory in an example, but I want to point out the three main rules of time-ordered perturbation theory. One is the factor of 1/2 omega j, where omega j is the energy of the line associated with each line. One is an energy deficit, right? The energy of each state, external energy of each state minus the energy in a state. And the other is the fact that there are only 3 spatial loop momenta that remain. So here's an example. So suppose you were studying light by light scattering, and you want to write the amplitude in time-ordered perturbation theory. Suppose you had, you order each vertex, right? So there are 4 vertices, I ordered each one of them. There's a particular time order that you pick for each vertex. Then a state lives between two consecutive vertices, right? So there's 3 states, C1, C2, and C3, and each state gets a denominator. So the first state gets a denominator, the external energy is P1 minus the energy of the lines in the state, so that's A and D, so P1 minus omega AD. The second state gets a denominator P1 plus P2 minus omega B and D, and the third state gets a denominator P1 plus P2 minus P3, which is P4, minus omega CD. So omega being the energies of the lines in the state. So time-ordered perturbation theory is just ordinary rewriting of perturbation theory, where these rules are different from ordinary perturbation theory. So this is completely standard algebraic manipulation. Now what I'm going to say in what follows is a lot of cool things follow if you take this algebraic manipulation of ordinary perturbation theory and sort of rewrite it. Okay, so just to be clear about what observables we're thinking of in the back of our mind, we're thinking about leptonic annihilation total cross-section and leptonic annihilation, as well as weighted cross-sections and leptonic annihilation. So these are inclusive enough that they have no PDFs and fragmentation functions and so on and so forth, and yet they're nice objects because they're completely finite answers, right? They're numerically finite objects. So we want to manifest that numerical finiteness and see where are power corrections in this framework, where answer is completely numerically finite, right? So as I said, time-ordered perturbation theory is formulated with a bunch of cuts. So you order all the lines, you order all the vertices, and there are cuts between vertices. So the drawback of time-ordered perturbation theory, as well as light cone-ordered perturbation theory, is that there's some cuts that are just bad actors. They're not real cuts of the graph. And so you want to first organize time-ordered perturbation to remove those cuts, because those cuts can not possibly be physical cuts of the graph. So here's an example of an unphysical cut. C2 is an unphysical cut. What C2 is it disconnects the left of the cut into 3 pieces, into 2 pieces. So it disconnects the graph, and this is a bad thing. And so what we'd like to first do is remove these unphysical cuts. But for those of you interested in power correction, C1 is the kind of thing where you start from the process in the vacuum, and then you feed that into the hard scattering. And you feed that into the hard scattering from the far past. And these are sort of, so these denominators corresponding to C1 are only pinched near the soft singularity, the soft singular point. And so these are well, they're not singular, but the soft subregion. So C1 are the sort of denominators that contribute to power corrections in a completely inclusive setting. And C2 is the kind of denominator you want to get rid of, okay, completely, because it's unphysical. So as I said, C2 is this unphysical denominator that had a lot of, it wasn't real. And so what I want to do in the next few slides is sort of explain why it's not a real cut of the graph. Suppose you're computing an amplitude on a cut of the type C2, right? Then my claim is that the amplitude vanishes, okay? And the amplitude vanishes for completely algebraically. So to see that, I've written on the time integral representation of time-ordered perturbation theory. So let me explain this formula a little bit and explain how to reorganize time-ordered perturbation theory to manifest this C1, C2 dependence, right? So let me explain this formula, because formula looks mysterious and formulas are boring to look at in presentations. So let me explain it a little bit. So each vertex now gets a time integral, right? So there's a dt alpha p there. Then each line, right? So from each vertex, a bunch of lines emanate. So each vertex alpha p gets an incidence matrix, right? So the incidence matrix, what it does is it's one if a line leaves the vertex. It's -1. It's 1 if a line j enters the vertex. It's -1 if it leaves the vertex, and 0 otherwise, right? So it's telling you whether the line is leaving the vertex or entering the vertex or not connected to the vertex at all. So now you just order these t alphas in time. You order them, and so this already you start seeing where this long time, short time separation is natural in time-ordered perturbation theory. it orders each vertex in time, right? So you order each vertex in time, and then you ask the question, okay, so I ordered each vertex in time, and then you do these time integrals, right? Because the time integral is minus infinity to the next one, and you generate the denominators that I just showed in the previous slide. Okay, so this is just a rewriting of the time-ordered perturbation theory denominators in terms with this algebraic time integrals. And so already you're able to sort of see that these time integrals are able to factorize locally long-time processes from short-time processes. So let's move forward and see what that means. So let's look at the integral representation of this graph. So I will be a little detailed in the next 2 minutes, and then I'll start skipping slides. So let's look at the integral representation of this graph, right? So the first graph, this example that we already looked at, there's a P1, sorry, oh, how do I go back? Okay, that's how I go back. Okay, so there's a momentum P1 entering the first vertex. That's the time integral for vertex 1. And then there's two lines in the first vertex, that is omega A and omega D, and that sits in the exponent for the vertex 1, and so on and so forth, right? So now, when you have disconnected components, the time integrals of the disconnected components factorize amongst each other, and the amplitude genuinely does vanish. So there's a believable statement. If you don't believe it, now you do. But okay, so now we can ask, what is local infrared finiteness? So local infrared finiteness follows from the fact that, so remember, in the example I showed you, there were two kinds of cuts. Vacuum cuts that were initiated in the vacuum, and these disconnecting cuts. But disconnecting cuts, I'm saying, I'm trying to emphasize that it's really bad cuts, but these vacuum cuts are important because they relate to power corrections. And so you ask the question, can you deform around these cuts? And Landau, you do some Landau analysis, which is done in our paper, and there you sort of find out that you can deform around most cuts except when a cut is pinched in a jet region, and when a cut is pinched in the jet region, you genuinely have to study those singularities. Okay, so here's a formula, an explicit formula, where we find who the pinches are, who is the singularities, and what the cross section looks like for E plus inclusive E plus E minus. So the first term is a total is like a total. Is a forward scattering like total cross section. First and last terms are like forward scattering like terms. So they have no pinches except the soft ones, and the middle terms have these jet-like pinches, right? So the middle terms have these jet-like pinches because they cut the graph, but the first and the last term they don't cut the graph at all. So so that's sort of physical picture of what's going on. There are terms that are like forward scattering that don't cut the graph and therefore don't have any pinches, and so on and so forth. Okay, so I was going to say something on the Landau analysis, but okay, I think I should not. So now let me say a few words about how to eliminate these bad cuts before I get to the good cuts. So it turns out eliminating these bad cuts sort of tell you how to organize these vacuum-initiated processes. And that's the point that I want to emphasize. So the organizing principle for eliminating these bad cuts in time-ordered perturbation theory is a structure called the post set, the partially ordered set, where you take any graph, any Feynman graph, and you order only vertices that are connected by lines. So one is related to 2, but one is not related to I, for instance. Okay, and now you go back to your integral representation for the post set instead of a time order, and you ask, okay, what happens now? Okay, so let's look at this example and ask this question. So what happens is, so this is a vacuum polarization graph without any cut placed in the middle, but we'll get to cuts being placed in the middle in a second. So you look at this graph, right? In this graph, you have 1 that's not related to I, 2 that's not related to O, but 1 and 2 are connected by line, and therefore they're related to each other, right? So it has an integral representation for the post set now, right? The partially ordered set. And when you look at this integral representation, you realize that you can do the one integral if you order the time integral, I mean, if you order 2 and O relative to each other. Okay, so you do the one integral. Okay, you have two choices: either 2 less than O or 2 greater than O, and you make both of these choices and sum of the choices. And here comes the magic of organizing these vacuum-initiated processes in the process of eliminating this bad cuts, right? So you did the one integral first to O, let's say, okay? You do the one integral to O, which means 2 gets placed after O, but then you generate this composite vertex at O, who lives his life at O, and the factor that relates to this composite vertex is this negative something. What I want you to notice is that this denominator now never vanishes except near a soft pinch. So the sort of obvious conclusion from this is that, as a fact of life, is that soft singularities only come from these composite vertices. Okay, so this is a sort of take-home message that I want to emphasize, that soft singular points are only ever coming from these composite vertices that you generate in this process. And so now suppose you do the next thing of integrating 2 to O, you generate yet another composite vertex, and this composite vertex has more denominators and so on and so forth. But again, these denominators have the form where they only vanish near the soft pinch and nowhere else. And the other denominators, as I'll show you, do not vanish near the soft pinch, and therefore you've locally at the integrand level factored the soft parts from the collinear pieces. So there's a recursive definition to extend this to all orders that I'll skip in the interest of time, and just show you a formula, flash a formula rather, about how these recursive definitions sort of enable you to write things in terms without the bad cuts. And in a second, I'll show you how the soft singular pieces factorize at the integrand level. Okay, so let's look at electroweak annihilation to do this. So electroweak annihilation has this weighted cross sections, and now we want to write this weighted cross section in terms of with these composite vertices placed everywhere. Okay, the crucial point I want to make in all this is that these composite vertices are only vanishing near a soft pinch, and the other cuts from the hard scattering are truly hard. Okay, so the vacuum organizes itself into 3 kinds of posets: either I is less than O is less than I, and I and O are unrelated. Okay, and so each of these has a formula that is in our paper, but here's the formula that it's also on the presentation apparently, but here's the formula that I want to point out, where what we've done is we've separated all the parts that have a Q dependence, the hard scattering parts that's in the last line, from parts that don't have a Q dependence, the parts that are only singular near the soft pinch, right? So using these composite vertices, you are able to separate at the integrand level pieces of the integrand that vanish near the soft pinch from pieces of the integrand that don't vanish near the soft pinch. And so this is sort of, I think, cool, because now you're able to organize these composite vertices, which in fact have operatorial definitions that we haven't fully worked out, and these composite vertices we're able to separate locally from the hard scattering. So now, okay, I was going to say something about contour deformations, but in the interest of time, I'm not going to. I'll just conclude by saying that, so now you can put this formula that I just flashed on a computer, and it's honestly, genuinely never singular, right? You can, provided you make the contour deformations that I was going to flash in a slide, intermediate slide, it's honestly, genuinely never singular. You separate out the soft pieces from the hard and collinear pieces, and you can integrate this locally in 4 dimensions. So one thing that we've sort of are working on is to write operatorial definitions for these composite vertices so that you can say what the subleading power corrections to a thrust cross section is, say. So that's sort of what we're working on. I think that's where I'll end. Yeah.
So, are there any questions? So then let me ask some questions. What will happen if you will have not a plus and minus regulation, but something which is renormalizable, where you have extra divergence on top of it?
Yeah, that's a good question. So what will happen is that you have this, so from the way that we think about it, you have these, you have sources of external momentum that start their life in the far past, and then they sort of join the hard scattering. So when, so the composite vertices for the source of external momentum where you have, say, incoming quark, right? These composite vertices will be the entire perturbative parton distribution function for this, because it showers in the far past and then it goes and interacts with the hard scattering. So that's roughly my guess. I haven't worked out exactly how the ward identities would go and hit the gluons in the far past, but that's roughly what I think would happen. Yeah.
Okay, and then is it possible to also formulate it for the process which could not be T-ordered from beginning, say like Drell-Yan?
Yeah.
Because when you have one current and our current, we're not T-separated.
Yeah, that I don't know. Formulating for Drell-Yan is a much harder question, because Drell-Yan, the issue with Drell-Yan is that the soft subregion breaks up into these other subregions that also go into the far past, like the Glauber subregion.
Yep.
And when you have a Glauber pinch, how to break up the Glauber subregion into different pieces that don't talk to each other in the far past, I don't know.
Okay,
yeah.
Thank you. Actually, this was my third question about Glauber.
Yeah, so the issue with, but it is a very interesting question, one ought to study it, right? And it's probably the place to study it, because the only proof I know, as I was saying, of how to cancel these Glauber regions is through this, is through time-ordered perturbation theory. So it may very well have a connection to that.
Okay, are there more questions? No, seems not to be the case. Thank you very much.
Thank you.
So, now we have time for discussion. Do we want to have some break now before it? Yep. So, generally at 6 we will have some welcome drinks, right? And before that we have time to discussion, and but I suggest to make indeed 5 minutes break and then come to discussion.
Make a 5 minutes break, and then everybody convene here in a couple of minutes just to have a rest from all the talk and think a bit about what has been said. And then the idea is to have a discussion session. I think this will be led by Alexei, hopefully. He will try to. And say whatever you have not asked before, you can ask now. So probably in 5 minutes. I don't want to waste your time anymore. See you in 5 minutes.